Hi everybody. Hi everybody. Today we are solving now this question. We have XY coordinate system, and then there is a cable which is infinitely long. So the cable is going up and down, and we would like to find the electric field at this point. We expect the electric field to be in this direction because of the symmetry, and the cable is very long. Okay, in order to find the electric field, we choose a small region here, and we say that since this is y direction, this is just dy, the thickness of this thing, and inside there is dq, just a little bit charge. dq is just a little bit charge, dy is just a small distance, okay? Just a small distance. Okay, so since we have this charge, it produces an electric field here in this direction, okay? And this will be dE. Electric field, if it is produced by dq, then it is dE. Then we say that the distance from this point to the point of concern, or at the point at which the electric field should be found, is r, and then this is y, of course. The height is y, and then say this is x, because this x direction, this y direction is very natural, and then this is angle theta that we will use later. Okay, so now dE, the dimensional, the magnitude of dE is given by k dq over r squared. Okay, this is just a regular thing that we know. So in order to find that, we have to just integrate this so that we get E. So when you integrate, okay, the electric field will be just k dq over r squared. However, this is going to be this electric field in this direction. But now, because of the symmetry, what we know that if you use exactly minus y distance right here, consider this charge, it will produce also the electric field in this direction, and then they will have both y components. So the y components will cancel each other, okay? So y components, Ey cancel, okay? But Ex components will survive. So that we have to get the x component. But the x component is just obtained by considering this angle. Exactly, these are the same angles. If they are the same angles, then Ex should be equal to E times cosine theta. Okay? Ex should be E. So Ex is just E cosine theta. I know it. So that's why to get the total electric field in x direction, I have to multiply this expression by cosine theta. So the new expression will be Ex will be just k is constant, take it outside, dq times, okay, cosine theta divided by r squared. But r squared is just y squared plus x squared. That's it. So now dq should be handled because this is the charge integration, but we have to do the geometric thing because we are used to getting the integrals in terms of x, y, or something. In this case, it should be y because the charge is distributed along the cable in y direction. So dq, remember that dq over the x dy is given as lambda, then we can use dq as lambda dy. So now electric field in x direction will be k, okay, lambda times cosine theta dy divided by y squared plus x squared. As you see, this is a difficult integration, or this is just r squared. This is a difficult integration because the integration is done with respect to y, but theta changes also, and y squared is there, so it's a complicated thing. Either we change this cosine theta to y something and try to solve, or do everything in terms of, write everything in terms of theta, so that you can get a simpler expression. So let's try the first one. When we try to write everything in terms of y, you have to replace cosine theta by something. But when you look at this geometry, cosine theta is nothing but x over r. So cosine theta is just x over r, so that this will be equal to k lambda x over r, okay? But r, there is also r squared on the denominator, so that it will be r cubed on the denominator, so there is dy there, so that this is going to be y squared plus x squared cube root. Okay, now if this was the integration for x, it would have been so easier. We would use the change of variables thing, but now since this is y integration, this is not easy. This is really not easy. So you have to use integral tables to solve this, so that this is a question mark. So this is not easy to solve. So what else can we do? We can write everything in terms of theta. So how can we do this? Okay, now look what happens. If y equals x times tangent theta, okay, y tangent theta is just y divided by x. It's just a cross side divided by the neighboring side. So if it is so, then as you see, this is an expression y as a function of theta. Then you can get dy by taking the derivative of tangent theta, which is just 1 over cosine square theta. Okay, cosine square theta times d theta. Of course, you shouldn't forget d theta there after taking the derivative. So not only this, but also we have r to be handled, because this is r square. So what is r square in terms of theta? So once we do this, then we can place everything to this integral and write everything in terms of theta. So now r square, first of all, cosine theta is equal to x over r, but in this case, if you do that, 1 over r square will be just equal to, okay, cosine theta square divided by x square. So cosine square theta divided by x square. Now, since x is constant in this integration, because x is not changing when you go up and down, x is always constant. It's nice because now everything is changed into theta by using this expression and this expression. Okay, good. So when we insert these things inside this integral, so ex will be given as just simply k lambda, okay? Lambda, where did it come from? Right there, k lambda, okay? The integral sign x times d theta cosine square theta divided by another cosine theta, and there is x square on the denominator. So these x squares will cancel that, and then one of the cosine squares will cancel. Wow, we end up with a very simple integration, k lambda over x times cosine theta d theta. It's brilliant because taking the integration of this, or taking the integration of cosine theta is just sine theta. When you do this and use the limits, now let's check the limits though. The first limit, okay, as you see, this angle is increasing if you go up and down. Okay, if you go up, this angle increases, and then the maximum when this is so far away, okay, the angle will be plus 90 degrees. And this angle, because the angle is measured from here, is positive, and the angle will be minus 90 degrees. Infinitely long wire. But infinitely long doesn't mean that really its dimension is infinitely long. Infinitely long means that if there is a cable and the charges are distributed, plus charges distributed there, then when you are so near to the cable, you can think that this is like infinitely long. We know this, we had discussed this earlier. So now this is sine theta, the result is from minus pi over 2 to pi over 2, this just gives you 2. So it's just electric field in x direction is 2k lambda over x, okay? So now if there is a wire here, okay, the electric field will be in this direction, and it will be given by 2k lambda over x, where x is this distance, and the charges are here plus. Of course, if this produces electric field, it produces electric field along this circle, just like the, if you consider a point, then all the electric field vectors will be aligned with this point, so circular direction, the electric fields will be as if the electric field is arising from this point charge. But this is true for each point though, okay? So the electric field will be some kind of homogeneous distribution along this wire. So it will be given by this. We had solved this as an example in the classroom. Okay. So this is one of the examples that I would like to discuss with you, so that I stop recording to let you ask me questions.